Hey everyone, Mr. Caldwell here, wanting to do a couple more examples as we develop our sort of abilities and strengths working with work and energy problems. So here's another example problem. Let's say that we have a 200 kilogram wagon that is going to go from 10 meters per second to 20 meters per second. The only way that that can happen is if something is pushing it, and it would obviously be gaining energy here. What type of energy? Think about it for a second. It's got motion, so it'd be gaining kinetic energy. So we can actually think about this and the role that work plays in a couple different ways. So first off, if this is all I give you and I say how much work is required for this, at first you might think, well, Mr. Caldwell, you just told me work was equal to force times distance. I don't know the force and I don't know the distance. But what we also know is that, gosh, if that doesn't seem useful, we do know that the total energy we have at the beginning plus or minus work, right? If we have an energy gain, it's probably a positive quantity. If we have an energy loss, it's probably a negative energy quantity. But that's going to equal the total energy at the end. So we can't forget the stuff that we've been sort of talking about now for the past class or two, because I do know that this object is going to have kinetic energy to begin with. And I imagine it is undergoing an energy change. So some work must be happening. And so then that's going to be equal to the kinetic energy that we have at the end. And so, well, what do we know? Well, kinetic energy is 1/2 times mass, which in this case is 200 kilograms, times the velocity, which is 10 squared. And I forgot to put the units there just to kind of make life a little bit easier. Better get my calculator out. And then we're going to set that equal to 1/2 times my 200 kilograms times 20 squared. Now here's an interesting point. We've done some problems where we had masses in every single term, and we've been canceling out the masses. Now look carefully at this. This work term does or does not have a mass term. Mass is here at the end, mass is here at the beginning, but there's no mass here, it's just W. So I would not cancel out my masses here. In fact, it would be absolutely dead wrong in terms of the mathematics. So at this point, I've got my calculator handy. I'm just going to go 1/2 times 200. So that's 100, 100 times 100. And for whatever reason, my brain just is not functioning yet, and neither is my calculator. That's 10,000. And remember that that is in energy, it's joules. And then this right here, we're going to end up with, I want to say that that's 40,000 because 20 squared is 400. And so now, to solve for work, subtract the 10,000 joules from each side. And we know that the amount of work done in order to increase the speed of this wagon from 10 meters per second to 20 meters per second, it would require 30,000 joules of energy in order to get this thing to change speed in that amount. Now, we can expand that and we can say, all right, well, what if we know that this change in speed occurs over a distance? This change in speed occurs over a distance of, we'll say, 15 meters. We can now use our friend W equals force times distance to figure out how much force did this require. And so at that point, you say, well, I know how much work it was. We know the work. We're trying to find the force, and we were given the distance. So the work is going to be 30,000 joules. We don't know the force, but it was done over a distance of 15 meters. So 30,000 divided by 15 gives us a force of 2,000. And remember, force is measured in newtons. So we would say force is 2,000 newtons. So that's another example of how we can start tying together the ideas of a work is an energy gain or a loss. We know that that's going to make that total energy equation more complete. And we know exactly how work is calculated because it depends on two things, the size of the force and the distance. Now let's look at a last example, right? A little bit of a complicated one, and then hopefully a combination of these help videos and you talking with your classmates about this stuff will enable you to do the energy homework number 3, the work and energy problems that you've got to do here today. So let's now take and think through a problem. And this involves pushing an object up a nice little incline. And if we think back to geometry, these right triangles, there are these things called Pythagorean triples. And certain combinations of numbers will always make a right triangle. So let's say this is a 5-meter tall, in essence, hill, and it's 12 meters long horizontally, but the actual length of the hill from bottom of the hill to top of the hill is the hypotenuse, which would be 13 meters long. And so we're going to take our, let's see, why don't we use a 15 kilogram box? And it starts at rest at the bottom of the hill. And we're going to have two things go on to it, two things go on with it. We're going to push upward with a force of, why don't we go ahead and say 200 newtons. And friction resists with a force. We'll say, we'll make friction small. It's not a very rough surface. A friction force of 10 newtons. And the question that we want to answer is, how fast is the box traveling? How fast is the box traveling at the top of the hill? So we've got some thinking to do, but the nice thing is we've done a lot of this thinking before. So we do have some forces and distances, but we also have a lot of energy stuff going on because we are going to look at this and say, well, what type of energy do we have down here where it's not moving at the bottom of a hill? So the total energy to begin with, that would be a 0. There is clearly some work being done by the push, and that would be an energy gain. So we're thinking in the back of our mind, well, that should be a positive quantity. And I always want you to write plus on the work term, because if you're careful with signs, the signs are always going to, work out. So there is a work term also associated with the friction. And we'll put numbers in here in just a second. And then we're going to say, well, okay, what type or types of energy are we going to have up here at the top of the hill? Well, if it says that it's got to figure out how fast, we're going to assume that there's some kinetic energy at the end. And it's got a height. So we've got a lot going on here. And now we can kind of dig in and see what this ends up looking like. So let's go ahead and figure out the work term for the push. We know that the force is going to be 200 newtons. Now I'm making that a positive force because when I push it up the hill, it's going to be giving it energy. It's going to be a gain of energy for the box. So a positive sign should make sense. And then I don't want to use the 12. I don't want to use the 5. I want to use the 13 meters because that is the distance over which I am pushing with my 200 Newton force. Now, how much work is friction going to do? Well, friction's kind of doing the opposite of helping. And that's why I was saying, look, if you're careful with signs, the signs will work out. The force is a hindering force. If I don't put that negative sign there, then it looks an awful lot like an energy gain. And it can't. It has to look like an energy loss. Again, force times distance. So I have to multiply my force by the distance over which that force acts. So that's going to be a 13-meter distance. And now we're getting real close. I'm going to go ahead and do 1/2 mass of 15 kilograms. I do not know my velocity. And then I think, well, what's the formula for potential energy? It's mgh. So 15 kilograms, I'm going to run out of space here, times 9.8 meters per second squared, times a height of 5 meters. Right? And again, if I look at this, this is one of these where we've got masses in some of our terms, but we do not have masses in all of our terms. So a very bad idea. Do not cancel out the masses, only if they are in every single term. So now we go ahead and just crank on our calculator, and I'm going to end up with 2,600 joules worth of energy here. And then we're going to do 20 times 13 minus 260. Half of 15 is 7.5. And then what do we get when we do 15 times 9.8 times 5? 735. And because that's an energy, that's also in joules. So 2,600 minus 260 is not that. If I could just put it in the calculator, right? 2340. 2,340 joules equals 7.5 V squared. And then think, well, what do I have to do to get V squared by itself? Two things are happening. It's being added to 735 and it's being multiplied by 7.5. So let's subtract the 735 first. And then that's going to give me 7.5 V squared. And then minus 735. And I really do appreciate you guys sticking with me here. Divide both sides by the 7.5. And then don't forget, that's not what V is, that's what V squared is. And so we're real close, and that's going to be 214. Last step, square root both sides, and we figure out that the velocity of this thing at the top of the hill ends up being something about 14.6. And since it's a velocity, that would be in meters per second. So that's a pretty hard problem. There's a lot going on there, but I'm hoping that that helps you guys in terms of understanding how to do some problems with work. And I'll see you guys again soon. All right, take care and have a great day.